Okay, let's get started. I think we are all here for an exciting event. I will be the host of the event. My name is Wolfgang Kedderle, and I'm a physicist, an atomic physicist at MIT. So let me just give you a brief introduction about the Aspen Center of Physics and also about our speaker. So I'm here in the library of the Aspen Center of Physics. The Aspen Center of Physics is a place where every year, without pandemic restrictions, 500 physicists would meet during the 16 weeks of the summer and come together in workshops. I have attended many, many times, and what it means for me is just an amazing atmosphere where you have spontaneous discussions, you interact with other physicists, you create new ideas. So it's an amazing working place, which is very inspiring. And I think many great ideas and publications have come out of this environment. What makes Aspen so special? Well, I think it is being away from home, being out of your office, being in another environment. But it is also the wonderful community we have here. Every lunch we sit together outdoors and talk about physics, but also about other things. And it is, of course, also this amazing environment in Colorado with the Rocky Mountain and in Aspen. Okay, so we have a public lecture series, and this public lecture series is named after Heinz Pagels. Heinz Pagels was a professor of physics at Rockefeller University, and over more than 20 years, he was a member and participant and officer and trustee here of the Aspen Center of Physics. Unfortunately, he died in a tragic mountaineering accident in 1988, and eventually this lecture series was instituted in his honor. By the way, this is now the last public lecture of the lecture series. The end of the summer. There will be a special lecture in December, which will be announced via email. I assume you are subscribed to the email from the Aspen Physics Center. And then in January, February, March, we have our usual winter series. Okay, so this is the Aspen Center of Physics. This is our Heinz Pagels lecture series. And now let me come to our speaker. So for every public lecture, we select a speaker out of the participants of the workshop. And the speaker is not only selected for his or her scientific accomplishments, but also for his or her skills as a communicator. And for this week, we selected Monika Schleier-Smith. Just a few words about her person. She did her undergraduate at Harvard, her PhD in 2011 at MIT, spent a few years as a postdoc in Munich, and since 2013, she is professor at Stanford. So she will explain what her research interest is. It's about atoms and photons, matter and light. And she has actually in her career done a number of amazing things with atoms and light. In her PhD, she developed methods to improve the precision of atomic clocks, to and find ways how to use quantum mechanics to make atomic clocks even more accurate. And in her research ever since, she was using light and atoms to create new and amazing forms of matter. Monika received for her accomplishments a MacArthur Fellowship in 2020, and just this year, the I. Rabi Prize in 2021. So maybe let me conclude by saying that I think Monika and I have a few things in common. The I. Rabi Prize is the American Physical Society Physics Prize given for a junior scientist. And I myself received this prize when I was much younger, 20 years ago. We also share our passion for atoms and photons. We are working on different kinds of matter, but atoms and photons, these are our Lego pieces which we use to assemble new objects and new forms of matter. And eventually, Monika and I also share the passion for running. When she was in Boston at MIT and Harvard, She actually ran the Boston Marathon 6 times, and I've also run the Boston Marathon multiple times. So with that, Monika, the floor is you. We are looking forward to your talk.
Thank you so much for this very generous introduction. One thing, Wolfgang, that you did not mention is that almost everything I know about atoms and photons I learned from you in my first year of graduate school at MIT in a tremendously inspiring course. And so I probably wouldn't be here without that, so thank you. So the title of the talk today is Atoms and Photons, from Fundamental Physics to Quantum Technology. I realized in looking at this slide that actually the order of my talk is almost the reverse. I'll start with quantum technology and work my way towards fundamental physics. So if you read a little bit in the news about quantum technology, or see the headlines, what you may have seen is that there are, over the past couple of years, there have been a few physical platforms that are reaching the regime known as quantum supremacy, where one has a system of quantum bits that is actually intractable to calculating its behavior on even the world's largest supercomputer. And there are, again, a few different hardware platforms that are beginning to enter this regime, ranging from solid-state circuits like the ones shown here on the right on the left, to systems of photons like the ones shown here on the right, and also systems of individually trapped atoms or ions controlled by laser beams. You heard the title of my talk has to do with atoms and photons, and so we'll be zooming in on the atoms soon. But before I get to that, I wanted to give a flavor of kind of what it is about these quantum systems that makes them so rich that one cannot describe them on even the largest supercomputer. And indeed, just something like about 50 quantum bits is enough to access this regime. So what do I mean by that? What is a quantum bit? Well, let's start with a classical bit. So on your classical computer, information is stored in zeros and ones that physically can be encoded by the orientation of some magnetic domain on your hard drive. So that sort of, I think of these as little bar magnets that point one way or the other, and that encodes a 0 or a 1. Quantum mechanically, information is stored in what we call qubits. And the way that these are different from classical bits is that they can, so I drew the classical bit as an arrow pointing up or down. The quantum bit could be an arrow pointing up or down, but it could also point somewhere in between. And we think of sort of the angle of this arrow, whether it's up or down or somewhere in between, as telling us the probability, if we measure the state of the quantum bit, of finding it to be a 0 or a 1. But in some sense, there's some randomness and probabilistic aspect of any measurement on a quantum system. So if the arrow is pointing down, that's a 0. If it's pointing up, that's a 1. But if it's pointing somewhere in between, there'll be this randomness, some probabilistic aspect. So in this sense, measuring the state of a quantum bit is a little bit like a coin toss. But it isn't just any coin toss. It's a very special kind of coin toss. And I recently actually had the privilege of having my explanation of this quantum coin toss actually animated in a little video. So let me start by giving you a little video telling you what is special about a quantum coin toss. The simplest quantum system is a quantum bit, which, like a classical bit, can be in the 0 state or the 1 state. The remarkable thing about a quantum bit is that it doesn't need to be in just the 0 state or the 1 state. It can be in what's called a superposition of the two. Fundamentally, it's unknown and unknowable whether the qubit is in the 0 state or the 1 state until a measurement is performed. And when the measurement is performed, it's almost like it has to decide. So I like to use kind of the analogy of a coin, right? A coin is a system with two states, heads and tails. And the superposition is a little bit like a coin that's floating in midair and it hasn't decided whether it's going to land heads or tail. So now the really neat thing, though, is that in a quantum system, you can have a phenomenon that's equivalent to me tossing a coin and you tossing a coin, and we repeat this experiment 100 times. And every time I get heads, you get heads. And every time I get tails, you get tails. But if I look at my tosses alone, the outcome always looks flat random. So there's this randomness, but there are correlations in the randomness. And that tells us that there's some information that I don't have. My coin toss looks random. You don't have it. but when we compare notes, there's actually some information there and not just randomness. So this idea of having information that's encoded in correlations, this is known as entanglement. And this is really the key resource for quantum technologies. Right, so this quantum coin toss is one where there's this randomness, but there are correlations in the randomness. And those correlations, known as quantum entanglement, give rise to the complexity of quantum systems. So just to give a bit of a flavor, why is it hard then to describe a quantum system on a classical computer? If I have two quantum bits, or two coins, two of these quantum coins, I need to keep track of the probabilities of 4 possible measurement outcomes, right? Heads, 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 tails, tails, heads, tails, tails. If I have 3, I need to keep track of the probabilities of 8 possible measurement outcomes, because these aren't necessarily all equal. In the quantum system, I could have a situation where whether that first coin lands heads is intimately linked to whether the subsequent ones land tails. If I have 4 quantum bits, I will need to keep track of 16 possible measurement outcomes, and so on, up to the point where if I had just 40, I would need to keep track of a trillion possible measurement outcomes and their probabilities and the correlations between them in order to describe an arbitrary state of this system. So this exponential growth in the amount of information needed to describe the quantum system has a number of implications. On the one hand, it's the reason why certain problems that are intrinsically quantum mechanical, things like calculating chemical reactivity, which has to do with the quantum mechanical behavior of electrons or the properties of materials, those can be intrinsically difficult to solve on classical computers. Because of this complexity of the quantum systems, the fact that they can be in a regime that is intractable to classical computation, we also think that they might more generally have the power to solve certain problems that classical computers can't. But at the same time, the fact that even to describe the system of, let's say, 40 quantum bits means keeping track of a trillion numbers, that is related also to the fact that it is not so easy to control quantum systems, and yet there's been rapid progress over the past few years. And I showed a couple of examples where individual atoms or individual quantum bits encoded in various ways are controlled at the level of these sort of tens that allow you to be in a regime that is intractable to classical computation, or even hundreds. So here's an example of some actually pictures from around the world where of a particular type of quantum system where the individual quantum bits are encoded in atoms that are optically trapped. And so here are some pictures where really each spot here is an individual atom. You can take pictures of them by shining in laser light and detecting the scattered light on a camera. And these systems of of optically trapped atoms, each one is trapped at the focus of a laser beam, are really remarkable in terms of their ability to be both scalable. One can have systems of 100 of them or hundreds of them individually controlled, and the ability to detect them at the single qubit level. The degree of control that one can get over these systems, thanks to, for example, being able to manipulate them with laser light, has applications in a number of different areas. One is building extremely stable clocks. The second, our measure of time, is defined in terms of the properties of an atom and measured by measuring the frequencies of oscillations within atoms. I mentioned computation. That is so far a work in progress, but each of these atoms can act as an individual quantum bit, and there is work towards assembling them into quantum computers. But short of building something like the computer on your desktop that can sort of calculate anything that is classically tractable, a sort of nearer term goal with these quantum systems is let's not build a computer that can solve all problems. Let's build some special purpose devices that allow us to simulate specific problems that are hard for classical computers. So we can perhaps build the hardware in such a way that it can allow us, with some controllable system of atoms whose positions we can specify, to mimic the properties of electrons in a material with a specified lattice structure. And that may allow us to solve a certain class of problems that are intractable by classical computation. So this area is known as quantum simulation, and all of these are directions that are being explored with systems of cold atoms. And one of the things that one needs in order to explore these directions is not only to be able to position and detect these atoms, but also to be able to control interactions between them, because interactions are what are necessary in order to generate this phenomenon of quantum entanglement, those correlations within the randomness. And I've shown you a couple of pictures here, which are showing systems of atoms or qubits, which are trapped in some sort of a lattice structure, and because of the interactions between them, they've organized themselves in a particular way. So in this case, the interactions favor those arrows I showed before, which I'll also call spins, favor them anti-aligning, pointing in opposite directions on neighboring sites. And so one sees some sort of checkerboard pattern forming from these interactions between neighboring sites on a lattice. Okay, so one limitation here is the connectivity of these interactions. So typically atoms will interact with each other if they're very close to each other. They might bump into each other. If the electron is in a highly excited state, an electron, one atom can polarize another atom, and that can give rise to some interaction between them. But all of these interactions, due to these electrostatic forces, will decay as a function of distance. So atoms tend to interact only with their neighbors, and that is actually a limitation. Why is that a limitation? Let me give you a classical analogy. So my classical analogy of why you care about the connectivity of interactions is the internet, right? The internet is what is allowing me to be in Palo Alto while you are perhaps in Aspen, and we can exchange information, we can share knowledge. And the fact that we have this connectivity where we can talk to anybody in the globe really changes many things compared to sort of the olden days where we talked only to our neighbors, right? And indeed, I spend an embarrassing amount of my time talking to some network of physicists distributed across the globe over the internet, as opposed to talking to my next door neighbor. But that really transforms the way that collaborations develop and that scientific knowledge evolves. So somehow, prior to the internet, what mattered was physical distance, but now what matters is distance in some network. And in a similar way in quantum systems, the way that one allows your quantum bits to interact and become entangled is important for the capabilities of the system. So just to give a few examples, if I have a system of qubits and they're on a lattice and they interact with their neighbors, that form of interaction naturally gives rise to a form of quantum entanglement that is a resource for computation. State that it's known as a cluster state, it's a resource for computation. But if you had instead a group of qubits where every qubit talked to every other, that form of interaction turns out to naturally give rise to a quantum state that is a resource for enhancing precision measurements, like those atomic clocks I mentioned earlier. If instead you have some random connectivity of the interactions between these individual quantum bits, it turns out that this type of a graph of interactions might allow you to observe a phenomenon akin to what happens to information that falls into a black hole, a phenomenon known as fast scrambling, where information is very rapidly goes from being in a local position to being completely distributed and hidden in quantum correlations and entanglement among these individual quantum bits. So that's an interesting graph if you'd like to explore simulations of gravitational phenomena in tabletop experiments. And lastly, if you have sufficient programmability of the interactions between your individual atoms or qubits, then you might be able to encode a particular problem, like some technologically relevant optimization problem, into the problem of minimizing the energy of your interacting quantum system. And so broadly here, the idea is that the structure of interactions governs the form of entanglement that can arise in the quantum system and the applications of that quantum system, be it towards computation, precision measurement, or simulating phenomena from gravity. So just to give a concrete example, though, actually, I'm going to go to this last column. How is it that the ability to govern the structure of interactions concretely could let you perhaps solve some real-world computational problem? This is, again, something where if you read a little bit in the news or perhaps the internet, you will find companies that tell you that they are going to solve your scheduling and logistics problems. They are going to help you optimize the return on your financial portfolio. Or I love this one, they will help you optimize fleet operations for holiday deliveries. So, I read these things and I always used to wonder, how do you take these like real world problems and actually map them into something that your quantum system could help you solve? There are lots of deep scientific questions, by the way, about whether quantum systems actually can help to solve these problems, what role this phenomenon of quantum entanglement plays. But also, to me, I was always wondering, how do you even take a real-world problem and map it onto a physical system? So let me give a concrete example that I can relate to because I'm an academic, and one of the things we need to do at a university is to schedule classes. So this is a logistical problem where, to give a simplified example, you might imagine having lots of students, all of whom have particular classes they want to take. And imagine that each student can attend, has there are two possible time slots that the university has for scheduling these classes. We'll keep things simple and imagine 2 time slots, a morning time slot and an afternoon time slot. Okay, and what you would like to do, you have a bunch of students and you would like to schedule the classes so that if a student wants to take 2 different classes, those classes will be in 2 different time slots. So one way that I could kind of represent this problem is to draw a graph where each vertex, each spot here in green is a class, represents a class, and each edge represents the number of people who want to take both of these classes that are connected by the edge. So I draw this graph, and what I would like to do is, if there's a very heavy edge, which means a lot of people want to take these 2 classes, then I should give those nodes different time slots, one in the morning, one in the afternoon. So one way I can think of that is sort of coloring the graph. Red is morning, blue is afternoon, and putting opposite colors if the edge is heavily weighted, if lots of people want to take those classes. Or equivalently, one can say I should sort of cut the graph in a way that cuts the heaviest edges, cut it into 2 pieces. Those 2 pieces are the morning and the afternoon time slot. So this problem of sort of coloring the graph or cutting it into these two groups to cut the heavy edges, this is called the max cut problem, and it's something that if I want to think about it physically, I could model this as a collection of qubits or spins. My mental picture is I think of these as little bar magnets that can point in one of 2 directions. And the heavier the edges, the more strongly the spins on those 2 sites want to point in opposite directions. So connected spins can lower their energy by anti-aligning. So these would be called anti-ferromagnetic interactions. The spins want to anti-align. And so if you can program this particular graph of interactions in your system, then that would give you a way of perhaps solving your problem by energy minimization. Okay. If you're not a physicist, but maybe an economist, you would think of it as I want to write down some kind of a cost function that depends on whether each site is in the +1 or the -1 state and minimize that cost function. As physicists, we think of it as minimizing the energy. And if we can physically make a system behave in a way where its energy is minimized due to the right type of interactions, then perhaps we can solve this problem. Okay, but so the tools we need are some way of encoding a qubit or a spin, some way of having interactions between arbitrary pairs, right? Because we'd like to be able to make ideally any graph, and control over what the strength of the interaction is, which encodes how many people want to take both of those classes. Okay, so that's just an example of how you would take a real-world problem and map it to a physical system. And one of the key challenges, as I mentioned before, is it's not so hard to get spins on a lattice to want to anti-align. But how do we get them to do this in a way where we have some arbitrary graph of connectivity? So this is something that we work on in my lab, and the way that we do this is we actually let photons carry information or generate interactions between atoms that are far apart. So by scattering a photon from one atom to another, those 2 atoms can talk to each other even at long distances. So that's one ingredient that in the simplest case, perhaps any atom could talk to any other. And we'd like to be able to have some way of controlling the system to decide which atoms interact. So before I get to sort of controlling which atoms interact, let me say a little bit more about how we would get photons to carry information between these distant atoms. So in the simplest case, if I think of each atom as a qubit, and in this case I represented the 2 states as this up or down arrow, and what I would like to do is I would like to convert, so if, for example, the left qubit is in the up state and the right one is in the down state, I would like a process where this left one can change its state by emitting a photon, and that photon gets absorbed by the other atom, which also changes its state. That can generate some kind of a flip-flop process where in a correlated way, these atoms change their states, and so that's an interaction between them that can be as long-ranged as the light can travel over long distances. Now, one limitation you might worry about is when this atom, when a photon leaves this atom, why would it hit the other atom and not fly off in some random direction? And it turns out that we can help increase the probability that a photon hits another atom by putting two mirrors around our system. So any light that is sort of between these two mirrors can make many, many round trips in a way that enhances the probability that it interacts again with another atom. If you like to think of light as waves, those waves can constructively interfere, and that constructive interference enhances the probability that these atoms will interact. So this is a very general approach to having photons carry information between atoms. And I'll mention that sort of variants of this are used in a variety of different contexts, ranging from kind of solid state devices like the one shown here that are actually used in superconducting quantum processors that I showed pictures of on the early slide, all the way to really macroscopic mirrors with atoms that are optically trapped between them, which is the type of system that I will talk about today. And which of these systems you use might depend on which application that you have in mind. One of the kind of features of these atomic systems is, I mentioned earlier, scalability. So one could have two individually trapped atoms, or one could have 100,000 atoms in a cloud, perhaps not individually controlled, but both of those are interesting for different types of applications. And actually one domain where these systems of atoms and photons already have a very strong track record is in this regime of sort of many thousands or hundreds of thousands of atoms. It turns out that these interactions mediated by light, mediated by photons, have already been used to make quantum states featuring entanglement, that key resource that I mentioned earlier in the talk. And in particular, one way that entanglement can be used, remember, the entanglement is correlations in the randomness. It turns out if you're trying to perform a precision measurement, by having those coin tosses not be random but be correlated, if one is more likely to land heads, when another lands tails, that can actually reduce statistical fluctuations in precision measurements, making states that are known as squeezed quantum states, where quantum noise is reduced in a way that enhances, for example, the precision of a clock. That has been done by using entanglement generated by photons in a cavity. So I drew that schematically here, like the hand of the clock, having some fuzziness coming from the randomness of the coin toss, but that fuzziness can be reduced. And so this is done in a regime where one has many atoms and they all talk to each other with the aid of light. And one thing I want to emphasize in these systems, it's been proven, for example, that 1,000 atoms are entangled. And you might say, well, how can that be? I told you earlier that even sort of writing down a description of 40 quantum bits takes a trillion numbers, and 1,000 would not fit onto a classical computer. And the point here is that somehow there's a relative simplicity to the types of quantum states that are studied in this case. I drew you a sort of schematic picture here showing some kind of a blob, which represents the orientation of the total magnetization of the system of atoms and the fluctuations around that coming from quantum uncertainty. So the fact that I can even draw a picture of this state of many atoms shows that in some sense it's a relatively simple state. And in this case that has to do with the fact that actually one arranges intentionally a system where every atom interacts equally with every other, and that simplifies the description. If you'd like to approach some of these other applications I mentioned, simulating phenomena from fields ranging from material science to quantum gravity, solving optimization problems, then you'd like to have some more control over the manner in which these atoms interact and which interacts with which other. And so I'll show the physical system where we work on that in my lab. Conceptually, it's really two mirrors 5 centimeters apart, in which we can optically trap atoms, and we have a lens below that we can use to take pictures of what's going on inside this optical resonator or optical cavity. All of this is inside a vacuum chamber, or inside an ultra-high vacuum environment, so that the atoms that we care about are well isolated from any other environmental perturbations. So that's this picture where you're looking at these two mirrors. And all of this is part of sort of a larger apparatus involving many lasers and mirrors and lenses, all of which are painstakingly aligned by graduate students. So you can see this is sort of part of a larger apparatus that fills a large room, where every component must be properly aligned to start to do some experiments. And once you have that all set up, the first sort of step in this type of experiment is a step known as laser cooling. I will not, it might be counterintuitive. People always ask me, a laser, why doesn't that heat? Why does that cool? Okay, so you can save that question for the end if you'd like, but lasers can be used to cool atoms to actually 10 million times colder than room temperature in my lab. That's a sort of fairly standard technique actually in our field. You can go even colder. Our distinguished moderator has even colder atoms in his lab, but this is good enough for us. 10 million times colder than room temperature is where we start. And that basically means the atoms are essentially brought nearly to a standstill rather than flying off in random directions. And that allows us to trap the atoms in an array of optical traps. And in this case, what we do is we take those atoms and we trap them in an array of about 20 little clouds of atoms. And in each of these clouds, there are a few thousand, just to give a sense of scale, a few thousand atoms. So this is not an individual atom. Earlier, I showed you pictures of individual atoms. Here, it's an array of little clouds of atoms. And we're going to ask, can we control how they interact? OK. So to show you, give you a flavor of what we can do with this system, I have to tell you a little bit more about what's going on inside each atom. Earlier, I talked about qubits, which have two states, an upstate and a downstate. It turns out in our system, our atoms actually have three possible states. So one where the magnetic moment points up, one where it points down, and one that has no magnetic moment. So I call them the -1, the 0, and the 1 state. So these have three different energies if the system is in a magnetic field. And so these atoms, when we want them to interact, what we do is we send some light into this optical resonator, right? That resonator is those two mirrors that enhance the interactions. We have a laser beam that we shine in, and a photon can bounce off one atom and off the other, and produce a process where those two atoms in a correlated fashion change their states. Let's just do that one more time. Right? So the laser beam allows a photon to scatter from one atom to the other. The first atom goes from the 0 to the -1 state. The second goes from the 0 to the +1 state. And so in some sense, by sending in light, we have a process where we can create pairs of atoms in the -1 and the +1 state. For every -1 atom, we need to get a +1 atom. And generally, until we measure, we actually wouldn't know which atom is in the -1 or the +1 state, whether it's the left one or the right one. So this is actually a mechanism that ought to generate entanglement, in the sense that this would be one of these, this would be like two coins where when one lands heads, the other lands tails, but you don't know which way any coin will land. Okay, so that's in our system the mechanism for making atoms interact. And to sort of see that that actually happens, I can show you an example of an experiment in this array of little clouds of atoms, where we start with all the atoms in that 0 state, the one with no magnetization, and we turn on a laser field that should make these atoms interact. And after some time, we measure how many atoms are in each of the three states, -1, 0, and 1. So we basically take a picture of the atoms in each state individually. The individual positions here would be telling me that how many atoms in a given site of this array are in a particular state, and the brightness says how many atoms. So this is showing actually many repetitions of the same experiment. And one thing that you'll see is that sometimes lots of atoms show up in the -1 and the +1 states. Sometimes most of the atoms stay in the 0 state, but we always see these correlations where when there are many atoms in the -1 state, there are also many atoms in the +1 state. And so this is kind of an illustration of this phenomenon where there's randomness. There's randomness in and how many of these pairs are created, but there are correlations within the randomness. Now, so far, I'm also showing you spatial information, how many atoms as a function of position, but the spatial information is boring. Basically, you see horizontal stripes. The whole cloud kind of acts in unison. And this has to do with the fact that so far, in what I'm showing you, every atom can talk to any other. A photon can travel from one atom to any other atom that we've trapped in this system. And I motivated earlier that one of the things that would be useful for applications, such as, for example, these optimization problems, is to be able to program actually which atom, or in this case, which little cloud, talks to which other one. So we'd like to start to control which of these clouds can talk to each other, control that graph of interactions. So we have a trick for doing that. And the trick for doing that relies on the fact that the energy differences between these three states depend on the strength of a magnetic field. And if we turn on a magnetic field that is varying, some gradient in a magnetic field, then we can have a situation where that energy difference depends on which site in my array I'm in. And the process of creating a +1 atom here and a -1 atom there does not conserve energy unless these two atoms are on the same site. So that allows us basically to have some meaning to the position of the atoms and let atoms only talk to each other if they're near each other. So that's the first step. Now we don't have everyone can talk to everybody. We have atoms can talk to atoms that are near them. Just to give you a flavor of kind of how do we see that in the experiment, we do a measurement like the one I showed you of how many atoms in each site or in each of the three states. And then we can measure some correlations, like if on site 10 there are more atoms in the plus state, does that mean there are more atoms in the minus state on site 10? So this is a so-called correlation plot where each pixel tells me correlations between the number of +1 atoms on a given site and the number of -1 atoms on another site. And the fact that these correlations are strong, there's this bright red line only on the diagonal, means that only on the same site are these interactions happening that are generating these correlated pairs. Okay, so that might not be so interesting. I told you there are other ways to have local interactions, like if the atoms were just colliding with each other. But what we'd like to do is be able to control more generally at what distance the atoms are able to interact. And we can do that actually by having what we need is a way to sort of bridge the energy cost of creating a +1 atom here and a -1 atom there. And we can do that by sending in light with two different photon energies or two different laser frequencies, so that an atom can absorb a photon of one energy and another atom can emit a photon of another energy. And so now by controlling the frequencies of light, or the energies of the photons that we send into the system, we can turn on interactions at some particular distance. And in this particular example, we've chosen that difference in photon energies in such a way that interactions are on at a distance of, let's say, 10 sites. And when we make one of these plots, we see strong correlations, a distance 10 from the diagonal that tells us we've done that. So we can turn on interactions at this particular distance. And we can vary the separation between these two laser frequencies in order to control the distance at which interactions are on. By the way, another way I like to think about this, if I send in two laser frequencies, and I look at the intensity of the light that I'm sending, I'll actually see a modulated intensity at a frequency that corresponds to the difference between the two. This is a little bit like when I tune my violin. I hear some beating in the intensity that tells me whether my violin is in tune or how far it's off. That frequency of the beating is something that one sees in this case on the intensity of the light. And so one way I think about this is by modulating the intensity of the light, we can turn on interactions at a distance set by the modulation frequency. Okay. So now we have this system here, and we're varying the frequency at which we modulate the intensity of the light, and we're turning on interactions at a controllable distance. We have very fine control of whether the interactions are at a distance of 9 sites, 10 sites, or 11 sites. But more generally, we can also now have a more complicated waveform in order to generate more interesting graphs of interactions. Okay. So just to give a couple of examples, let me actually show you how do we know what we've done. What is the connectivity of the interactions that we've created? So one way we can actually do this is we turn on some particular modulation waveform. In this case, we designed it so that atoms interact with other atoms that are 3 sites away. We measure some correlations between the states of atoms versus their positions. And then we can ask, actually, based on the experimental data, if I were to assume that there's some representation of these sites in some effective geometry in which correlations and interactions are local, what would that geometry look like? So we can actually take the data and extract some representation of effectively sort of how are these atoms connected and how far apart should we think of the sites as being if we had local interactions. And in this particular example, we can make, for example, a system that acts not like a single chain, which is the physical geometry, but like 3 independent chains, which has to do with the fact that interactions are at distances of 3 sites. But we can also do fancier things, like here I chose my laser waveform so that I have interactions between neighboring sites and interactions between, let's say, 9th neighbors in a chain of 18. So what I think I'm doing is making some connectivity that looks like this wheel here. While we're at it, we can also choose the type of interaction. Do the spins on these sites want to align, or do they want to anti-align? I'll indicate that by a red or a blue bond. And then we take a picture of our system. We take many pictures of the system in many experiments. We measure these correlations. And we ask, what is the best geometric representation of the graph that we have created? And actually, in this case, it turns out just by analyzing the data, what pops out is a Mobius strip. What's going on here, if I sort of say in what I described earlier, I have these sort of bonds between neighbors, and I've connected things in a ring. And in fact, here, that ring is sort of this one edge of this Mobius strip that winds all the way around until it comes back to the original point. So we have this very kind of exotic geometry that we can realize just by controlling the waveform of the light that we send into our system. In this particular case, I said neighbors want to align, opposites want to anti-align, and so we can think of this as those spins are kind of winding around the wheel in terms of their orientation, or winding once as we go around the edge of this strip. So, and you can now, again, sort of vary the waveform of the light that you send in. So these different purple curves are showing the intensity of the light as a function of time, and realize a physical system that even though the sites of my atoms where they're trapped are unchanged, just depending on the laser field I can control, does the system behave as if it's connected in a ring? Is it connected in a Mobius strip? Is it connected in a cylinder? These are all things that we can tune. We can build this interaction graph up by controlling the laser field. Okay, so what can you do with that? One thing I mentioned earlier, actually, was this idea of could you perhaps use these programmable graphs of connectivity to solve optimization problems, like the scheduling example I gave before. And one of the interesting things we noticed in this system is that, in fact, even though all we're doing is initializing the system in a simple state with no magnetization, and suddenly turning on some interactions and watching what happens, it's not immediately obvious that this should be a way of minimizing the energy of the system. But actually, we can set our system up so that there is a slight cost in energy for creating a +1 -1 pair, which to conserve energy, that allows the system to lower its interaction energy by raising the energy internal to each individual atom. And so, in fact, what we observe is that these atoms, if I think of each atom again as an arrow or a magnetic moment, and I look at the texture in which they are arranging themselves, they are in fact arranging themselves in a texture that minimizes the energy of the system, or at least appears to match a low energy state of this system. So for example, if we have these triangles, and every site wants to anti-align with its neighbor on these triangles, this is actually a phenomenon known as frustration. 2 of them can anti-align, but the third one wouldn't know what to do. And so the spins will organize themselves into some sort of 120-degree angles. That's the closest they can come to anti-aligning. And that's something that we measure in the experiment. And it's an indication that one direction that this system could, in fact, be pushed further is to explore, can one solve some problems that are classically hard that can be mapped to these interacting spins using the quantum dynamics. So I mentioned, quantum control and engineering useful entangled states with interactions mediated by photons. I mentioned optimization. Earlier, I touched on directions in harnessing these systems also to simulate phenomena from other areas of physics. And I would like to give a concrete example from the domain of actually asking, can we build tabletop quantum systems that can simulate phenomena having to do with gravity? And that So why would we even think to do that, or why would we want to do that? Well, the idea that this might be of interest comes from this question of sort of how do we start to think about these systems of entangled particles where even tens of particles, the full description can't fit on the classical computer. One way theoretically that one often goes about trying to sort of get a handle on the description of such a quantum system is to map the structure of entanglement onto some geometric picture. Use geometry to help us understand the structure of entanglement. And to be specific, there's a concept where certain quantum systems, let's say this two-dimensional system of qubits shown here, have some simplified description in terms of a higher dimensional system, so a system with one additional dimension, in curved space, where you can think of that curvature as coming about from gravity. So there's some mapping between quantum systems in some low dimension, 2 spatial dimensions in this case, to a system with gravity that curves space in 1 additional spatial dimension. This is called holographic duality because of this idea of sort of an extra dimension emerging in the description of the system. And the idea is that this somehow gives away, this geometric picture gives away for sort of distance in this geometry to encode something about the strength of entanglement in the quantum system. And to sort of come up with this geometric picture, one starts with the individual quantum mechanical degrees of freedom and tries to come up with some simplified description by a process of coarse graining, describing small groups of spins instead of the individual spins. And from that mathematical process, a geometrical picture can emerge. So this kind of is a sort of theoretically elegant idea where there are a few examples that can be written down in paper where what really emerges is something that can be described as a geometry that can arise from gravity. But it raises the question, is this picture that entanglement can be represented by curved space and gravity, is this a more general picture that might be useful for visualizing quantum states that we realize in the lab or that arise in nature and can help with this challenge of describing quantum systems? And on the flip side, does this story mean that actually gravity in our universe really might be a phenomenon where the microscopic ingredients are actually quantum mechanical and gravity somehow emerges from quantum entanglement? Does that actually describe gravity in our world, or is this just a nice mathematical description? So I certainly won't answer that deep question today, but we've been interested in building toy models in the lab that can help to kind of explore these ideas. And in doing so, I've been very fortunate to have, I think a lot about quantum mechanics. I actually don't know so much about gravity, so I've been very fortunate to have collaborators who can teach me about gravity. And one in particular was Steve Gubser, a theorist at Princeton, who tragically actually passed away in a climbing accident a couple of years ago, much like the person for whom our lecture series is named. But Steve actually was trying to understand kind of what is the mathematical structure behind the reality that we experience as smooth space-time, but which in all likelihood is discrete at a fundamental level. And that idea that perhaps in all likelihood space-time should be discrete comes about from the existence of quantum mechanics, which implies some natural shortest length scale. So Steve was trying to understand this mathematically. And before I say more about how he was doing this, I just have to mention, actually, because this is an Aspen lecture, that Steve actually grew up in Aspen, and the last time I saw him was in Aspen. And so I have to just share this really brief video recollecting an Aspen conference in 2019. This is a video of Steve, and this is mini Steve. One of the things I actually love about this video is that he made this video after skiing in Aspen. It ends up with the line, "Watch out for the tree." And actually a tree is a structure that Steve was thinking about deeply as a potential way of resolving this idea that our notion of space-time is smooth, but perhaps fundamentally space-time ought to be discrete. So it turns out that a tree graph can actually be viewed as kind of a discretized version of a space with curvature, with negative curvature, that could describe actually space-time curvature arising from gravity. And the basic concept is that one can imagine having some physical system that has, let's say, n sites that live on the leaves of this tree graph. The key thing about the tree graph, by the way, is that the number of sites on the boundary is exponentially larger than the depth. And so, you know, if I have just, let's say, if I wrap it around onto a circle, if I just have a circle, then the ratio between the radius and the circumference, or let's say the diameter and the circumference, is just a factor of pi. But in this case, actually, of the tree graph, the geometry has to actually be curved in order to explain the fact that I only need a logarithmic number of steps in the depth of the tree compared to the number of sites on the boundary. So that's the sense in which this represents a curved space. And the question is whether there are situations where this type of a tree graph representing curved space could emerge as a natural description of the quantum correlations in this physical system of some number of sites. And actually I will say, mention a few experiments where people have actually built quantum systems that literally are interacting on a tree graph in circuits that you can pattern, just building the circuit that way. But the question that we were interested in is, are there situations where that tree graph emerges as the natural description of a quantum system as opposed to being sort of programmed in? And so there was a sort of a toy model that we came up with together with Steve Gubser, in which one has an array of sites. There are interactions that are not just local, but actually at distances that are powers of 2. That might seem exotic, but it's something that we can do easily in our experiment. And the conjecture was that depending whether those interactions decrease or increase with distance, the system might behave more like just a chain with nearest neighbor interactions, or like something where the best description of distances in the system to describe the quantum correlations is something like this tree graph. So, you know, we decided now recently to just program this system into our experiment, because all it takes is sending in the right laser modulation waveform. We can measure the correlations between the states of the atoms on the different sites of our array, and ask, is the system behaving in a way that would be described by this emergent geometry of the tree? And so, as before, we measure some correlations in the quantum system. It turns out that if you just sort of look at correlations as a function of physical distance, they look very strange, and they don't just decay. They're strong at distances that are some powers of 2. It doesn't look like a natural physical system where correlations are local. But if you actually rearrange effectively the sites in your analysis in a way that matches the ordering of the sites on this tree, then the correlations smoothly decay in a way that corroborates the idea that the tree is the right effective description of this system. And perhaps more importantly, just based on the experimental data, we can do something like I showed you before for these things like the Mobius strip, ask what is the best sort of geometrical description of the sites in the system. Roughly, they might be organized on some kind of a ring. I'm showing you this here for 2 cases where the interactions either shrink or grow with distance. But then we ask, which of these sites are most strongly correlated? Ideally, we would measure which are most strongly entangled. We don't directly measure entanglement in our system, but we ask where are these correlations strong? And we draw links between the sites that are strongly correlated. We treat them as a bigger site, and we keep drawing those links. And what emerges just from the experimental data is actually this tree graph that can be viewed as this kind of discrete version of a curved space with gravity. So one of the sort of added features of this system, we can tune it from something that acts just like a linear chain to something where the best description of kind of distance in the system is distance measured along the tree graph. But we can also sort of tune to some intermediate regime by varying just a single parameter that says how do the interactions decay in the physical system as a function of distance. And in that intermediate regime, it turns out if you ask which sites are strongly correlated to which other sites, there's sort of no natural way of cutting the system in half so that there are halves that are uncorrelated, but rather everything is strongly interacting with everything else. And that has a behavior that is similar to one I mentioned very early on in the talk. We think, we sort of conjecture that this should have a behavior where, because every atom interacts so strongly with every other, if you were to initially encode some information in one site, it would very rapidly become kind of hidden in these complex correlations and entanglement between the different parts of the system. And that actually is a lot like what is conjectured to happen to information that falls into a black hole. It's not lost, but it is very quickly hidden in complex quantum correlations. There's a nice quote from Stephen Hawking saying, what happens to the information is like burning an encyclopedia. Information isn't lost if you keep all the smoke and ashes, but it is difficult to read. And the reason it would be difficult to read is it would be hidden in those correlations between exponentially many possible configurations of the quantum mechanical system. So this could ultimately then be a toy model for exploring in the laboratory this process of what happens to information that falls into a black hole. So those are a few directions that we hope to explore in the future. What I've shown you today is a physical system where, by letting atoms talk to each other with the aid of photons, we have really a high degree of control over the graphs of their interactions that is relevant for a variety of different directions, ranging from encoding specific problems and harnessing the physical system to solve them, perhaps by energy minimization, to simulating phenomena from quantum gravity, to engineering in a controlled way entanglement as a resource for applications ranging from enhancing precision measurements to computation. So with that, I want to just briefly acknowledge that there's a wonderful team of graduate students and postdocs, as well as collaborators, who I am constantly enjoying interacting with and learning from, and who made these experiments that I showed happen. And here are a few of those people in the lab. And with that, I will conclude, and I hope that there will be questions.
Yeah, thanks, Monika, for this amazing talk, which took us from, single qubits and single photons into the world of black holes. So I assume there will be questions, and if you have a question, please raise your hand and I will call you. Barbara, please unmute yourself.
Hello, this is Michael, Barbara's husband, and I would like to return to the diagram in which there were two atoms, each with a mirror behind them, and talk about this process of one atom communicating with another. So you've got this cell and bound by mirrors, and I gather you shoot a laser beam in there. Presumably the two atoms in this cell are at equal energy levels, and the laser beam enables one atom to kick out a photon, which then presumably is resonating between the two mirrors. At that point in time, are both atoms at the equal energy state? And if so, wouldn't it be equally probable for the atom that emitted the photon to reabsorb it and hence not be communicating with its adjacent atom? There must be a fatal flaw in my thinking somewhere, but I
don't think there is a fatal flaw in your thinking. So if an atom, is this the diagram you wanted? I think this is one of a couple diagrams like that.
Yeah, that'll do, yeah.
That one will do, yeah. So if an atom, basically an atom, what will happen is an atom absorbs a photon from this control laser and then emits a photon into the resonator, so it sort of scatters that light from the control laser. And there are different things that can happen. First of all, that photon can be absorbed by another atom, and there are, in general, I showed this with two atoms, but in general there are actually in our experiments many atoms, any of which could absorb that photon and flip its spin. So one possibility is, as you said, that the original atom kind of reabsorbs the photon and nothing happens. That is one possibility. But all of these other possibilities are also there, that a different atom flips its spin. And so the net effect of all of that is that there is some probability that a different, and actually just to sort of maybe show this picture again, Even if I ignored the possibility of the first atom reabsorbing the photon, there are certainly two possibilities in terms of which atom gets flipped up and which atom gets flipped down. So yes, sort of, you're correct. There are a number of different things that can happen, but the net effect in this simple example would be to create kind of what we call a quantum superposition of the left atom being in -1 and the right being in +1, or vice versa. If you do this for, let's say, the right amount of time. And in general, it's also possible, as you say, though, for the atoms to come back to their initial states. Does that answer the question?
It sort of does. There's maybe a brief follow-up. If you've got multiple atoms in there, which I believe you said you could somehow track, do you understand the probability that any given atom will absorb that photon? And is that what you see in your experimental results?
Yeah. So in the simplest case, the probabilities. So sort of physically, they depend on things like what is the light intensity at the position of a given atom. But we take pains to make that as uniform as possible. And in that case, essentially, every atom is basically equivalent, and all of those probabilities are the same. And that's kind of what's going on in some pictures I showed, where you see that sort of, you see these relatively uniform looking sort of stripes of brightness that show that sort of across this cloud, atoms in one site or atoms in another site are roughly on average equally likely to undergo this process. That's true until we start playing these games with introducing a magnetic field gradient that changes the probabilities of that process happening in a way that depends on distances between the atoms.
Okay, let's move on to the next question. Charlie, please unmute yourself.
Yeah, I come from a mathematics and computer science background, and one of the questions that I'm interested in is, in classical computation, you have the Turing machine to model that process of computation. Is there something like that? In other words, that you have a quantum Turing machine concept, so that you also would have non-computable algorithms, or so that, maybe I'm not being very clear, but basically, does the conceptual structure of computation transfer from classical to quantum via the Turing machine idea?
That's a very good question. The structure does transfer. You might ask, are there differences in terms of how it transfers? And I'm not sure I have a great answer to that, unless you ask a more specific question. But there is a generalization to quantum systems.
Well, let me be a little bit more specific. Is there such a thing as non-computable functions in quantum computation?
Is this related to something like the halting problem?
Yes, Einstein's problem, right?
Sort of whether the Turing machine stops.
Exactly.
I actually don't know off the top of my head. It's a very good question, it's a very good question for a quantum information theorist, and I will look it up afterwards, but I don't know off the top of my head. I don't know whether our moderator knows.
Nope, I don't know either, but so maybe that's why we should move on to the next question. Connor, please unmute yourself.
Hi there. First off, I just have to mention that I have wanted to go to Stanford since I was 5. So, okay. And my second question, does this have any relation to, it seems like all the stuff with connections and trees could be tied back to neural networks in some way? Do you see any connection between quantum computing and neural networks?
Definitely, yeah. I think, so there are actually various different connections that are explored. So one direction is actually, can you use classical neural networks to describe quantum systems, or to come up with efficient representations of quantum mechanical states? But another question is sort of, if your neurons are quantum bits, right? What can the quantum neural network do that the classical one can't? And so there's certainly research in that direction. It's something that in these systems of atoms where one can program the structure of interactions, it certainly feels a lot like sort of varying those interactions in time, and the connectivity in time, one could actually build up something that is a lot like a neural network. And it's something that I think I've always thought I would like to learn more about and think more about, and it's a direction that I think is really natural to explore in these systems. So, yeah.
Okay, maybe let me ask a question for myself. Monika, so what capabilities would depend on whether you have single atoms on a site, or whether you have, I think you mentioned about hundreds of atoms on a site. Of course, hundreds of atoms gives you a much better signal to noise ratio for some initial experiments, but when is it really crucial to advance to single atoms?
Yeah, this is a really great question. One place where I mentioned early on in the talk the difficulty of computing the properties of quantum systems of even small numbers of quantum bits. And in our case, here I showed you something with 18 sites. It would be reasonable to scale it to something like 60 sites, where if there were a single quantum bit on each site, that would directly be in that regime where it's intractable to classical computation. It turns out that actually having many on each site actually makes the system a little bit simpler to describe, and in some sense, in understanding and controlling the system, it's helpful to us that it operates in a regime where we actually, it turns out, can predict at least sort of the initial early time behavior of the quantum system by using some description in terms of what I would call a semi-classical description, where one describes thinks of the system a little bit like those bar magnets I showed, with some quantum noise in with the direction in which it's pointing, for example. So there are semi-classical pictures that allow one to calculate things about the system. In terms of so it's in this interesting regime where with many atoms, one certainly can generate entangled states, and that's something we're currently working on in the lab, is kind of quantifying the entanglement in the system, and ask questions already about, for example, can the system be harnessed as a resource for these optimization problems? I think that's actually an interesting question, even in this regime of many atoms per site. That said, I think if you want to sort of say, I'd like to be thinking more in terms of sort of standard paradigms of computation with quantum circuits of individual qubits, and certain problems in, let's say, simulating solid state materials, where there's an individual quantum spin on each site of some lattice structure. There are a number of directions where it would be nice to be able to do the same thing with individual atoms. And also actually, ultimately for this question of like looking at information scrambling in black holes, the cleanest system to think about that in would be one with a single quantum bit on each site. And the sort of experimentally, in terms of reasons why we're not doing that yet, there are kind of, I would say, two. One is, like you said, it's nice to get the signal to noise of many atoms. And the other is that we actually win in terms of the interaction strength compared to kind of the rate at which photons can be lost from the system by having many atoms. And so there's sort of a technical direction in terms of optimizing the strength of the atom-photon interaction to get to a regime where one could look at individual atoms. And that's
thanks for the answer. We have to wrap up soon, so let me call Steve Harris for the last question.
Monika, since every atom could talk to every other atom, you are forming very large superposition states. How large, as a practical matter with limitations, how large are the superposition states that are formed? And this is quite related to your question, to Wolfgang's question. To what extent could you really control the superposition state by using polarization or the temporal form of the incoming laser beams?
Yeah. So first of all, I think maybe it's worth saying something about kind of the form of the state that's generated. And roughly, so it's this type of state where I know something about kind of how many spins are up and how many spins are down, but I don't know which spin is in which state. And in general, sort of the first, so one way of sort of quantifying that is seeing that quantum fluctuations are squeezed, that sort of coin toss noise is reduced. And so in that sense, and all atoms participate in this, right? But in terms of saying something about how strong are the correlations in the system, one way of quantifying that is saying how much would you expect those quantum fluctuations to be reduced. For kind of our parameters, if you were dealing with just one of these individual clouds, it should be reasonable to have that be something like a factor of, let's say, about a factor of 10. But also one could control kind of the structure, the spatial structure of the correlations. And that's a little bit harder to think about, right? But have correlations of a similar flavor where if there are more spins up on one site, there are more spins pointing down on the other. And so and in principle, the structure of that, what is most natural for us to do with this trick of modulating the laser field is to have basically any form of correlation that depends only on the distance between sites. That is the sort of natural thing for us to do. And so it can be within a given site, it can be between all sites that are 4 apart, or some combination of those things. Did that answer the question?
Yes, thank you.
Mm-hmm.
So I'm sure there would be many more questions, but I think every good thing has to come to an end. So let us all thank Monika for a fascinating talk and an interesting discussion. And I wish everybody a good evening and bye-bye.